So, welcome to the sixth week of Engineering Mechanics live interactive session. So, this week we are going to look into the rigid body dynamics. Until now, we were looking at the point particle dynamics and kinematics, but today we are going to look into rigid body dynamics. So, I hope already you have watched the lecture videos where concepts have been already explained. Unlike point particles, where we only need to consider Newton's second law, here we also need to consider it's a modified form of Newton's second law, where two equations appear, Euler's equations for rigid bodies. So tracking the center of mass using Newton's second law and a modified version of that in the for the rotation about the center of mass. So we'll go to the first problem. The uniform bar of mass 10 kg given below sinks about A. If at an angle, if at an instant, theta dot, which is the angular velocity of the rod, is 5 radian per second, and theta being 45 degree, compute the force supported by the pin in newtons at A at that instant. So basically, I have to find the reaction forces acting at the pin joint A. So it's just a rod which is swinging. So you could try this out. I'll wait for a moment, then I will explain how to do it. So first of all, you need to draw the free body diagram. So just a rod, because unlike a normal pendulum, this rod has an extent over which the mass is distributed. So we can assume it to be through the center of mass. The entire weight is acting. That's one of the force acting on the body AB or the rod. And now at the point A, there can have reaction. So there can it's a pin joint, so it can support both horizontal and vertical reaction. So it will have, let's say, horizontal reaction Rx and a vertical reaction Ry, which are unknowns at the moment. And we know this is swinging about the point A at an angular velocity which is given, which is 5 radian per second. And so we have to compute the reaction forces Rx and Ry. Basically, we have to find the resultant, magnitude of Rx and Ry, the resultant of Rx and Ry. For that, we individually need to know Rx and Ry. So these are basically the forces acting on the system. Now One thing to remember is that if you just release the also angle theta is given to be 45 degree, which we use. Length of the rod is also given, which is 0.9 meter, 900 mm, which is 0.9 meter. So one thing to remember is that when we release this, it will not just move with an angular velocity, it will have an acceleration as well. So the angular acceleration, which is not given, take it to be alpha, radian per second square. We need to evaluate that. So for that, first we need to write the torque balance equation, or let's begin with the force balance equation. That's what we need to write. The sum of the net force acting on it should be equal to total mass times acceleration, and now this is acceleration of the center of mass, because this is not a point mass, it's a rigid body. Now we need to write the component equations. I hope I am audible. If not, please inform me so that I can raise my voice. So if you look in the x direction, we have a Rx, the horizontal reaction at point A, and there is no other horizontal force acting on it, so this will be mass times its acceleration in the horizontal direction, let's say Ax. And vertical forces, there is a reaction force Ry acting at point A and an mg. So yeah, this is total mass is I used to denote small m, so let me use that. mg, which is equal to mass times acceleration in the y direction. So here we are just writing so here Ax and Ay are so we are writing this equation for center of mass. So basically I assumed the components of center of mass velocities as Axi and Ayj. Okay, so the coordinate system is like the normal. We choose x direction is the same, y direction is this. So that's what I wrote here. So these are two equations, and so Ax and Ay are unknowns. Mass is given, mass is given 10 kilogram. So we will use them later. So this is so G is also known. So Ax and Ay are unknown. So we cannot determine Rx and Ry from these equations. Let name it as 1 and 2. Now what else we have? Equation. So we have the torque balance equation. So total torque acting on it is equal to mass times not mass, the moment of inertia times angular acceleration vector. Now you might have watched the lecture videos where professor told you had to take, it's better to take the total torque or total moment acting about the center of mass, so that moment of inertia about the center of mass times alpha. So this you can follow. So I insist you to try this same problem using this formula, but because he haven't shown how to use the same formula with other points, I'm going to not complicate this, but as you may aware that if I choose any other point to take the moment, then this formula is no longer valid unless that point is a fixed point, basically not moving, don't have any linear motion. So but this formula is valid if the torque or moment is computed about the center of mass of the body, even though it is accelerating. This formula will be valid, and this formula will be also valid if I take the torque moment about some other point which is fixed. So here if you see here, so the center of mass, which let me denote as capital G, which is somewhere in the, it's actually in the middle of the rod. So I can use this formula about G. So this formula will be valid. So where I have to compute the torque or moment about G. Similarly, the center of moment of inertia I have to compute about G. Then this formula will be valid. Or I can choose about A, which is a fixed point, which is not moving. Then correspondingly I have to take the moment of inertia about the point A. The same formula will be again valid. But if I try to write the same equation about B, the point B, which is actually now moving, so I could do like this, which is equal to moment of inertia about B times angular acceleration alpha of the rod. But I had to account for the extra terms which due to the fact that B is in motion or accelerating with respect to the center of mass. So I hope this concept is, so because of that, this formula will not be valid about, this formula will be simply not valid. We have to consider the extra terms. I hope that concept is already clear from the lectures. Just that in the lecture it's only shown how to solve this problem using the first formula, like if you choose the center of mass. But you could choose any other point also if you but that point must be a stationary point, not a moving point. So I choose here A, but I insist you to try the same problem by doing the same way as the professor did in the course. By considering G about point G, try to solve this. Take the moment and try to solve this. So here I am considering the point A, so we will just go with that. So if you see here, I have chosen the alpha value to be clockwise direction. So I will just take the clockwise direction moment as positive. So as a result, this equation, you can see if I consider the moment about point A, the Rx and Ry will not contribute to moment because they are passing through A. Only the remaining force, which is mg, going to contribute to the moment. So it is mg times the moment arm, and you can see the moment arm is this distance. So which is basically, so you can see this is L by 2, L is the total length of the rod, and L by 2 times cos theta. So this length is L by 2 times cos theta. It's projected in the horizontal plane, the L by 2 distance. So that is the distance of the point G, the center of mass, from point A. So it's mg times L by 2 cos theta, which is the clockwise moment created by the weight mg, and this is the only moment acting if I take the moment about point A, and this should be equal to IA. IA is the moment of inertia of the rod computed about point A. So assume the rod AB is rotating about point A in the plane, then what will be its moment of inertia about point A? Now I don't know whether you people have already learned it, but let me give the value. It's ml square by 3. If I were computing the moment of inertia about the center of mass, that is Ig, it will be ml square by 12, where m is the mass of the rod, L is the length of the rod. But because I am computing the moment of inertia about the point A, which is one of the end point, so it will be ml square by 3. So this is a value of I about A times alpha. So because I have chosen already alpha to be clockwise in direction, I don't need to consider the sign because both the moment and the alpha value are consistent with the sign convention I chose. So now if I solve for alpha, because that is unknown here, I can get alpha being, so basically m will cancel, one of the L will cancel, so its value will be 3g by 2l times cos theta. So if I evaluate, if I can substitute all the values, 3 times 9.81. So you can choose g to be 10 also, but I just use 9.81. Sometimes in the question it will be specified you have to use 9.81, otherwise you can choose 10. Okay, and the length is given 0.9 meter times cos of theta, where theta is given to be 45 degrees, so I'll give that value, and you will obtain around 11.561 radian per second square. So now you have evaluated the angular acceleration by using the torque balance equation. So one of the equation of motion you have used it to solve for alpha, but the other two equation of motion 1 and 2 are still unknown because you evaluated alpha. That has nothing to do with ax and ay when you see from this perspective, but now the thing is that you have to consider the kinematics, which we have learned in the last week. So if you see the kinematics, so basically the acceleration of point A in a vector sense, you can write its acceleration of point C, not C, I mean center of mass, let's say G is the center of mass, right, plus acceleration of A related to G, right. This is basically the relative acceleration equation. Now you can expand this. There will be two components of the acceleration of A with respect to G this time, which will have a normal component and a tangential component. So the normal component will be a centrifugal acceleration, and the tangential component which will be an angular, due to the angular acceleration. So it will be the alpha vector times the radius vector 2a measured from G minus the centrifugal acceleration, which is omega, whatever the angular velocity of the rod, omega square times rag. So this we have learned last week, right? So why we want to use this? So we know acceleration of A should be 0, right? Because A is not moving at all, because A is a fixed point, right? So that's the purpose. So A is not moving, so left hand side is 0. Now acceleration of G, which is basically AXI and AYJ, the two unknowns which we need to evaluate are here, plus alpha vector. Alpha vector, if you see here, alpha I defined to be, so we have evaluated the magnitude of alpha to be 11.561 radian per second square, right? But alpha vector is actually acting clockwise, right? So because we have chosen the coordinate system to be right hand way, as I have shown here, this means that the k vector, the x cross y vector, which will be out of the plane coming towards you, that's how the k vector. So basically the alpha vector is whatever the magnitude of alpha is there. So what I mean by that is that the alpha vector should be whatever the magnitude of alpha times k cap, but in the negative sense, because it's clockwise, right? Because in the right-handed system, the counterclockwise direction is a positive sense. Because I have chosen the right-hand system for x and y, the way I chose alpha here is clockwise, so that the actual alpha vector will be negative of that. So it will be by the convention. So this will be minus alpha k vector, that is alpha vector, cross the rag vector, which is the position vector of the point A measured from G. So now that will be, let me show that vector, which is from G. Okay, excuse me. You can see this is the vector I want to. Now this is rag vector. Okay, so rag vector, which is having a magnitude of L by 2. We can see that it has a length of L by 2, and its component in the x direction is its projection in the x direction, which is cos theta only in the I direction. But because the vector if you think the coordinate system is about the point G, because we are measuring the position vector to A from G, right? So you have to consider the coordinate system starting considering origin being the G, the center of mass location. And you can see that this RAG vector, which is pointing in the second quadrant, so that means its x value should be negative. So it's minus cos theta I in the x direction and sine theta in the y direction, but that will be plus because it's a second quadrant, right? So it's a sine theta j vector. Okay, so that is RAG vector, so which I am going to use here now. So RAG vector will be L by 2 times minus cos theta I plus sine theta j. Okay, so we have written the second time. Now final time is minus omega square, again RAG vector. So let me do one thing. So same vector, coming here, but now there is no cross product, it's direct multiplication. So this is one of the equation. This is actually a vector equation, so it contains two component equations in I direction and j direction. So you will basically get two of these equations with the two unknowns, ax and ay. You can ideally solve for them. All other quantities here are known. Alpha is, we just evaluated to be, it's 11.5, and theta is already given, which is 45 degree. L, the length of the rod, is given. So omega is also given, 5 radian per second. So we can actually solve this to obtain the acceleration ax. So let me skip and write the result. So I hope you guys could directly evaluate it. So I am not spending time there, I am just writing the results. So the acceleration in the x direction, you can get it to be minus L by 2 omega square cos theta minus L by 2 alpha sine theta, comma acceleration in the y direction is L by 2 omega square sine theta minus L by 2 alpha cos theta. So you can substitute the values of L by 2 omega and theta. So yeah, omega is 5 radian per second and alpha is, we just evaluated. So you can solve for ax and ay. Then you go back and substitute in 1 and 2. We will get the reaction force in the x direction is mass times acceleration in the x direction. And if you do that, you will get this value of the reaction force is minus 116.337 Newton. And the reaction in the y direction, from the second equation you can see it's mg plus may. So that you will get it's around plus 140.862 Newton. Now the net reaction force, the magnitude, which is rx square plus ry square, the whole square root, and you will find it to be 192.69 Newton. So that's the answer. I hope I conveyed the way to solve this problem. I insist you to try this out using, as I mentioned, taking the moment about the center of mass instead of the fixed point A. But remember, when you do that, so right now we got alpha explicitly here when you just solved the moment equation. But when you solve, because when you take the moment about the point A, the unknown forces Rx and Ry are passing through the point A, so that their moment is not coming in that moment equation. But if you were writing the equation about the center of mass, then both Rx and Ry will appear in the moment equation as well. So the moment equation will remain as a unknown in that case. So what you have to do is that keep that equation there, so that alpha will still be an unknown. The alpha you cannot explicitly solve only using equation 3, which is the moment equation, but you have to keep it as an unknown. But when you later come, simultaneously you may able to solve equation 1, 2 along with the acceleration equation using the where you substitute the moment equation relation. So you will able to solve all the unknowns there. Okay, so I hope that is clear. Any questions in this part? I am audible, right? So any comments whether you understood or not understood? Good, so then we will move to the next problem. So water acceleration A of the collar in meter per second square will result in a steady 60-degree deflection as shown below. The mass of the ball is 10 kg. The mass of the rod is 3 kg. And the rod is 0.5 meter long. Assume the collar to be frictionless. So basically it's saying that we have a hanging pendulum on end of which has a mass which is 10 kg, but it's not a normal pendulum. The rod also has some mass which is 3 kg, and now the collar is accelerating at a value of value is not given. We have to find the value of what the acceleration is, such that the the entire system will make an angle with the vertical to be 60 degree. So we have to find the A. So it's like you can think of something hanging in a car or something, and you accelerate the car, you will see that this hanging thing will go backside, right? Will make an angle. This you guys can have you would have experience in this thing. So just try to solve. Basically, at least you try to draw the free body diagram. I will explain how to do this anyway. So I'll give you a moment to draw the free body diagram just for the pendulum. Okay. So did you try the free body diagram? So basically we have a system. So a rod is there, and at one of the end we have a mass. So the mass is 10 kilograms. So because of that, it will experience a 10 g force downward through its center of mass. And now remember, the rod is also having a mass, so through its center of mass another force will be acting, which is 3g. At point P, okay, now it's connected to collar by a pin joint. So pin joint can support two reactions, Rx and Ry. Okay, now the system is accelerating with an acceleration A in the horizontal direction x. So this is the free body diagram. Things to remember, okay, there is an angle theta, and the theta is given to be 60 degree, which we use later. We have to find what is acceleration A, which is an unknown for the moment. So let us name this system with this being the center of mass of the rod. Let's say this point, the end point is P, so let's this point be Q and this point be R. Now remember, okay, let us come to that in a while. So first we will anyway write the force balance equation. Net force acting on is equal to mass times acceleration of the center of mass. So this is a force balance equation. So if you write the horizontal direction, we have the Rx force acting in the horizontal direction, and there is no other force acting in the horizontal direction, is equal to the mass times acceleration in the horizontal direction. So mass is the total mass, okay, of the system. You can see here the rod has a mass of 3 and the ball has a mass of 10, so total is 13. Acceleration center of mass is here. So this is one of the equation. Next equation is that the vertical force balance equation, which is there is an acceleration horizontal reaction, vertical reaction Ry acting at point P, and there is a 3g acting at the through the center of the rod, and 10g is acting at point R. The center force will be balanced by the total mass 13 times the acceleration in the y direction, and you can see it's not moving in the y direction, so there is no acceleration in the y direction, so this term is actually 0, which you can rewrite as Ry is equal to 13g, which is the second equation. Now Ry we already know it's 13g, because g is a non-value, you can put 10, so you'll get around 130 Newton here. But Rx, which is 13a, where a is an unknown, so Rx is still unknown, so you can say that Ry is solved already, but Rx is unknown. So okay, these are two equations we got from the force balance. So to determine A, we can use equation 1, but Rx is still unknown, so we have to find Rx for that. So we will try to write the torque equation. Torque is equal to mass times acceleration, again I am writing mistake, I times alpha, the torque vector. Now here I will anyway follow the center of mass concept, so we will write the equation about the center of mass. Now this rod, so if you think, so if it's accelerating in the horizontal direction, in the positive x direction, you know this how the motion of, you can intuitively think the ball will move backwards, and there will be an angular velocity and angular acceleration in the clockwise direction. So I'll choose this to be alpha. This direction it is basically clockwise direction is accelerating with an angular velocity being alpha. Doesn't matter, you can choose counterclockwise as well. When you solve, you will get alpha being negative, you will realize, okay, the direction I chosen was not correct. So then you can come back and correct it. So it's just a convention. because I chose clockwise because I already know that intuitively also you can identify it will be anyway clockwise motion. So you will get alpha being positive when you solve it, which is matching with the assumption of this being clockwise. So anyway, we will write the moment of inertia about the center of mass and the torque. So first we have to evaluate the torque about the center of mass. Okay. First of all, where is the center of mass? That's one thing that we need to identify. So it's not a simple body; it's a connected body. So the rod has a center of mass at Q, and the mass has the ball has a center of mass at R, center of the ball, and it's not nothing specified about the ball, the size or something. So you can assume it to be a point ball, has a mass of 10 kilogram. It don't have an extent. A radius is not given for the ball, so that you can assume it to be a point ball. Still, how will you evaluate the center of mass? So I don't know whether you guys are already familiar with this concept of center of mass and all, but I'll anyway go through this. So we have the system. Okay, this is the system. Now I'll denote the center of mass of each of the system, each of the particles. So which is the rod has center of mass at its center, and the bob has at its center. Now you can consider a coordinate system. So let me denote the points. So this is R, this is Q, and this is point P. Consider a coordinate system which is measuring the length from P. Let's call that coordinate system as R. So the center of mass location, R center of mass, is given by sum of masses times the radius divided by sum of masses. So here if you write the mass of the first body times the center of mass of the first body plus mass of the second body times center of mass of second body by mass of the first body plus mass of second body. Here you can think the first body being the rod, whose mass is 3 kilogram, times center of mass of the first body, R1. So you can see R1 is the distance measured from P, because we are choosing that as a coordinate system. So P2, the center of mass, which is at Q, right? So it's the length PQ is the distance R1, and you know which is L by 2, which is half of the length. I'll just call it as L by 2 for the moment. And M2, which is mass of the second body, which is a bob, which has a 10 kilogram, times R2, which is the distance to the center of mass of the point mass, which is at R, capital R, right? So that is this distance. So earlier this was R1, and now this is the distance which is R2, which is measured from again point P, which is actually the total length of the rod, because at the end of the rod, so think if this was a big ball, then still its center of mass is located L distance from the rod, but depending on how we have placed the bob, we may have to add the radius of the bob as well. But here the bob or the mass don't have an extent, size is assumed to be point, so it is exactly located at the end of the bar. So its distance, center of mass, is actually exactly the L distance from the end P, so which is 10 times just L divided by the total mass, which is 3 plus 10. So now you can simplify, you will get 11.5 by 13 times L. This is our center of mass. Now you can substitute the value of L. L is around 0.5 meter, but I am right now not substituting it. But the idea here is that the center of mass, r center of mass, which is again the position to the center of mass measured from the same coordinates center we started with. So it is the location of the center of mass measured from P, and you can see it's 11.5 by 13 times the total length of the rod, and you can see it's around if I evaluate that quantity, it's around 0.88 times the length of the rod. So it's almost 88% of located far from the end P. So I can locate that around somewhere here. This will be the center of mass location G, and you know its location is measured from the end P being 13.5 L by 11.5 L by 13. So let me mark that here. This distance is our center of mass that we have now evaluated. You can choose a different coordinate system. Instead of the point P, you could have chosen the point Q to be the origin where you have measured, but you will ideally locate the same location G with respect to whichever coordinate you have chosen from Q or from P. Just that same location you will identify or you measure from different points, so you'll get different values, but it will be the same location. Now the thing is that now we have located the point G. Okay, so now the thing is that we have to evaluate the torque about point G. Before that, let me tell one thing. So ideally we should have evaluated the, so for this equation, the moment balance equation, we should also need to know the moment of inertia I about this center of mass G, which will be contributed from the rod part as well as the point mass part. But for this particular problem, we have an equilibrium, right? So basically you are thinking that the collar is moving horizontally, so that we are finding at a particular angle the center system is like attaining an equilibrium. So in that equilibrium sense, so basically initially it will have an angular acceleration, and then it will come to a particular angle and it will stop there for this particular acceleration. So the acceleration it expects, so basically it will come to a dynamic equilibrium, but without an angular acceleration. It will be static at that location. So in that particular case, the angular acceleration will be 0. So it will be like the whatever you have done earlier, without the forces and torques. Sorry, without the this is basically the kinematics you will come to. So you will have the kinematic equilibrium, the net force or the net torque is equal to 0. Now you can evaluate the torque about the center of mass that I have evaluated, which is the location G. So so G will be, so if you come here, so G will be somewhere here in the rod. Okay, so about the point G, we have to evaluate the moment. So so all the forces, which is the weight 10g, 3g, rx, ry, all the forces about the center of mass will create a moment. Now you start with 10g. 10g is creating a moment which is actually counterclockwise. Now 10g is located at a distance, this much distance. This is a moment arm for 10g, and which is basically so if I extend, this angle will be 30 degree only, right? Because this was 60 degree here, this angle, so for that to be 60 degree, this angle should be 30 degree. Now whatever the distance RG, whose cosine projection, horizontal projection, so 10g times the distance RG cos 30, which is the moment created by the point mass, and now 3g, which is acting at Q, which is creating a clockwise moment, so the sign will be negative of that. 3g times QG, again projected in the cos 30 direction. Now Ry is creating a counterclockwise moment, so Ry times PG, the length which is projected in the horizontal direction cos 30, which is the momentum. Now Rx creating a clockwise moment, so which is Rx times the distance PG, but now it's the momentum is projected in the vertical direction, so it will be sin 30. Okay, so this entire moment, they should be equal to 0. That is what the moment equation says, because it's not accelerating when it is reaching the equilibrium state. So we want to find that acceleration such a way that it reaches the equilibrium to making an angle 60 degree. So that's the criteria. Now here RG, you can see RG is the distance from the end of the rod to the center of mass, G. So you can see here the end of the rod is, so measure everything from P. R is located L distance away, right? Minus, and the G is located 11.5 by 13 L. So if you do that, you will get 1.5 L by 13. And L you can substitute always. L is given as 0.5 meter. I am not substituting that, you can substitute. And the distance QG. So let's say this is the third equation. So QG is a so Q is located L by 2 distance from P, because it's a center of the rod, right? And G is located at 11.5 L by 13. So you have to subtract them. So 11.5 by 13 L minus L by 2. So yeah, you can evaluate that. I'm not evaluating that, which is a known quantity. Now come back. So we have RG to be known, QG is to be known. Now PG, that is the distance, the point P measured from G. Now you know we are measuring the distance to G exactly from P, that the center of mass location we already evaluated, which is 11.5 by 13 times L. We don't need to subtract anything, we are directly getting that. So these quantities you can evaluate and substitute back to equation 3, where now the unknowns in the equation 3, so all other quantities are known except Ry, Rx. So 2 unknowns are there. Okay. And you can see Ry will be evaluated at second equation. So Ry is also known. Now only unknown is that Rx, and Rx along with equation 1 we can solve. So you will able to solve for Rx and A simultaneously from equations 3 and 1 after substituting equation 2 in 3. So you will obtain the solutions like this. When you write the solution, you will get Rx being 221 Newton, Ry being 98.1 Newton, and the acceleration, which is around 17 meter per second square. So you have to accelerate with an acceleration of 17 meter per second square. to keep this entire system to be 60-degree angle. So that's how we do it. Is this clear? Any question? So I have an identical problem, one more problem. So here acceleration is given, a is equal to 2.5 meter per second square. We have to find the angle theta. Now, unlike the earlier case, we only had one rod, and at the end solve 3. Okay, is Rx find on solve 3? Yeah, so if you see equation 1, 2 and 3, equation 2 is already solved to get Ry, right, because it's just 130 Newton if you substitute, so Ry is known. Now if you substitute back to equation 3 that value, then you can see only unknown in equation 3 is Rx, right. Now you can so it's a single equation, you can solve for Rx from equation 3. Okay, use that Rx in equation 1, divide by 13, so you'll get acceleration E from equation 1. So basically they are just solved. Yeah, so now so I have an identical problem here. Acceleration is given, now we have to find the angle. The other ways, procedure will be same, just that the body, earlier we had just the first rod and the mass at just the end. Now the rod of 0.5 meter, now we have the identical rod, one is joined with this welding or some other means, so fixed 90-degree angle they bend, and the mass is at the end identically. It's again, so you can think of the free body diagram will be something like, you have an L shape like this, you have a 10G acting here, 3G acting here, 3G acting here. Now point P is here, and there are some other points about which the force is acting. So at point P you will have a horizontal reaction Rx and vertical reaction Ry. Now so this is making an angle theta which we need to evaluate, and you can see this angle will be 90 minus theta, because this angle need to be 90 minus theta for this to be 90 degree. And you follow the same procedure, you have the force balance equation. That does not matter, because the orientation of the body doesn't matter there. Now the torque balance equation, again the net torque should be 0 for it to be come to an equilibrium position without an acceleration. Now point to notice here is that the body is not just distributed along a line, unlike the earlier case. It's now bent, so it's a center of mass. Locating the center of mass is important. Or you could try using the fixed point, finding the moment about the fixed point P. Okay, actually point P is not fixed, it's actually accelerating with the accelerator. So better you evaluate the center of mass, and it will be somewhere here. It will be actually outside the body. The center of mass will be somewhere located at this particular location. Excuse me, yeah, center of mass will be somewhere here. Okay, it will be outside the body. And so you have to choose a coordinate system for that. So it's a little involved problem, but if you're able to solve this, I'll anyway give the solution. So not a detailed solution, the answer is 37 degree. So with the free body diagram look like this. You have to locate G same way, but just M. So right now you have to, unlike the earlier case where it's just along the line of the body. We know because only the mass is distributed along the line of the body, right? From P to R, all the mass is distributed along the line. It will be just located, the center of mass will be on that line somewhere. That's why we use only R to evaluate that. Now that we have an extent which is the body is extended in two different directions, we need to consider a coordinate system. So you can start the coordinate system somewhere. I mean, this is a different coordinate system. This is just for evaluating the center of mass. So let's say this is the body. So this is a point P. You have one center of mass here, another center of mass is here, and another center of mass is here. Each is of weight 3 kilogram, 3 kilogram, and 10 kilogram respectively. Now you have to consider a coordinate system. So you can choose this be one of the coordinate system. Let's say this is x direction, this y direction. Not to confuse with the xy we choose for the forces. So let's say this is capital X and this is capital Y. So we have to evaluate so mx1 plus mx2, so m1x1 plus m2x2 by m1 plus m2. Actually here three masses are there, so m3 x3 by m1 plus m2 plus m3, you will get the x bar. Similarly the y bar, center of mass y, is m1 y1 plus m2 y2 plus m3 y3, the whole divided by m1 plus m2 plus m3. So basically x1 is the center of mass of the first body, x2 is a center of mass, location of second body. Similarly the third body, x3. X bar is the center of mass of the system of all the masses in the x direction, measured from whichever coordinate system you choose for x, measuring x1, x2 and x3 from the same origin of the coordinate system. So let's say this is the point I chose to measure the x direction. So for example, if you look at the first body, which is this body, it's a x1 center of mass location. From that distance is just L by 2. And this is second body, its center of mass is located 0 from this particular value, right? Third body is also located 0 in the x direction. Now in the y direction, if you see, the first body has no y displacement with respect to that coordinate system. So y1 is 0, y2 is L by 2, y3 is this distance which is L. So I hope that is clear. So you can evaluate, locate the center of mass x bar and y bar. You will get it somewhere here. The center of mass is located. Okay. Yeah, I think I could give the exact location of the center of mass. Give me a second. Yeah. So if you say this is the center of mass, from this end, this is around 11.5 L by 16, and this end you will measure 1.5 L by 16, where L is the length of a rod, okay, which is 0.5 meter, I think. So you can locate the center of mass. Then repeat the process as I done earlier. Just that you need to take the moment about G due to all the other forces. So it's a little involved, but it will be a better exercise for you to remember how to take the moments and all. Okay, so any question here? So we'll move to the next problem. So the uniform rectangular slab is released from rest in the position shown. Determine the value of x for which the angular acceleration is maximum in terms of b. So I hope the question is clear. Try to draw the free body diagram, then I will explain how to do this. So basically here all the problems we are using the two Euler's equations, which is a modified form of see, always you can take the moment about g, doesn't matter. Always you can take a moment about a fixed point, doesn't matter. Your equation will be same. Just the net torque is equal to I times alpha. Excuse me. What matters is that, so now you have to specify the point about which you have to take the torque. So if you take about g, then I should be about g. If you take about a fixed point, I will denote that using f, then I should be about the same fixed point alpha. Now alpha should be the same because it's a angular acceleration same body, just that the torque and the corresponding I values are changing. Because unknown usually will be the alpha, we have to solve for that. Now if the torque you are taking about a moving point, which I notating using m, then Im alpha not alone will satisfy. You have to have some extra terms which is involving the acceleration of the center of mass. So because of that, if you just do this will be wrong. You can write this, but you have to account for the extra terms. Better we don't do this at all. We will not take moment about any moving point. We will use these two equations, and specifically the first equation about center of mass will be better. You can always use this. Doesn't matter. Even though the center of mass is moving and accelerating, this is always valid. And about fixed point, nothing need to be care. If there is a fixed point x is in the system, you can do this. The thing is that, sometimes some problems it will be easier to take a moment about a fixed point. In certain problems, it will be easier to take a moment about center of mass. So wherever possible, we will. It's better to take the moment about the center of mass and consider the entire system about the center of mass. But in certain problems, the equation will be greatly simplified if you consider a fixed point. For example, in the previous problem, if you have seen, we could have taken the moment about the point P, but you can see the point P is actually moving with an acceleration a, so we cannot just do that, because if we take moment about P, the Rx and Ry will not create a moment. You can just solve it easily. But finding the center of mass, we have to actually do that, finding the center of mass, which is at G, and we would have we need to take the moment about the point G. That's why this equation 3 was a little long, right, including Rx, Ry, everything, but this is still correct. We don't have any other fixed points in the system, so we have to do this. Otherwise, if you have taken the moment about P, then we have to consider the acceleration a and all into account, and the equation won't be this simple. It will be a little complicated to get the final result. So I hope that is clear. But coming back to this problem, here you can see the point G, which is the center of mass. So we can take moment about G, or you can take moment about the point O, which is a fixed point, right, not moving at all. So here I hope you have drawn the free body diagram, but anyway, let me draw it here again. So we have a rectangular box whose center of mass through which its weight is acting. Mass is not given, maybe not required, so mg, and there is some location, there is a normal reaction R is acting, and the separation between them is x, which is an unknown, we have to find x such a way that the value of x, what is the value of x? For that, the angular acceleration is maximum. Now, what will happen when you release this block? It will try to rotate about O, right? So, it will have an angular acceleration. So, you know, it will anyway go and rotate in a clockwise manner. So, I will choose that convention for alpha. It's angular acceleration alpha. And now, so this is its equilibrium equation. Give me a second. Yeah, so we will write the moment equation. The net torque is equal to I times alpha. Okay, now this is valid about G, so we could do that, or about any fixed point. So I am going to choose the fixed point O, about which I am going to write this expression. So first of all, so the advantage of doing this is that you can eliminate the reaction forces, as you have already seen this in the kinematics as well. But here you have to be careful. Unlike in the kinematics, you have an acceleration on the right hand side. So this equation, as I mentioned in the earlier sometime before, like you have to be very careful when choose. So if you don't have a fixed point, so the moment about which you are taking that point, if that is not fixed, then this equation is not valid. Or this equation can be written always about the center of mass. So the reason why we choose any fixed point is that we can eliminate the reaction forces, which is always an unknown. So we have to solve for it and then come back. So here R is an unknown, the reaction force. So to eliminate that, I'm checking whether the point is fixed or not, the point O, and it seems it is fixed, so that this equation is still valid about O. So I am just going with that. So the moment about O, so because I have chosen the alpha to be this way, clockwise way, so I will choose the clockwise moment to be positive. Okay, that convention. So the only force which is creating the moment about O is mg, which is at a distance of x, right? So the mgx should be balanced by I about O times alpha. So that's our only equation. Now we have to solve for I0, not I0, IO. We have to know what is the moment of inertia about O. So this is a rectangular block. So usually they should give the moment of inertia, but for rectangular blocks and all, we can actually evaluate it easily. So I don't know whether you guys are aware of this. So if you have a rectangular block of, so let's say breadth B and height h, and center of mass will be at location B by 2 and h by 2 location, right? So I about the center of mass G will be m times B square plus h square by 12. Okay, now we want to evaluate the moment of inertia about O. So there is parallel axis theorem that we will use here, which is basically Ig, and you are shifting the location to this distance. So Ig plus the mass times distance square, where d is a distance to that particular location where we want to evaluate the moment of inertia. So Ig is just m times b square plus h square, which is b by 2 the whole square, the whole divided by 12, plus m times d square. Now d, you can see here, which is diagonal in a sense. This distance is b by 2 and this distance is x. So d square will be, from Pythagoras theorem, it will be x square plus b by 2 the whole square. So you can simplify this and you will get IO being, let me write the expression. You will get it's m times b square over 6 plus x square by 2, I think. No, by 2 is not there. Yeah, just m. Okay, so this is a IO. Now come back to equation 1. You can substitute this. See, x is an unknown, we have to evaluate that. So mg times x is equal to alpha times m times b square over 6 plus x square. So I have used capital M and small m intermittently. Don't confuse, just the mass of the body. Probably I will write the capital M to avoid the confusion. Okay, now you can, anyway, the m is getting cancelled, so we really don't need to worry about m. So you can write the acceleration, angular acceleration, to be gx divided by x square plus b square over 6. Now we have to find the x values in terms of b, for which this acceleration alpha will be maximum. So for that we are just do the calculus thing. D alpha by dx should be 0 for finding the extremum values, right? G is a constant, so you will just see it's x square plus b by 6 times 1 minus x into 2x by x square plus b by 6 the whole square should be 0, and you can solve, you will get the critical value of x being b by root 6 from this. Basically only numerator you have to equate to 0 and solve for x. So any question in this? So this is the critical value in terms of b, the distance x, for that the acceleration alpha to be maximum. So here we didn't use the force balance equation. Usually we use the force balance equation to solve for the unknown forces. We have unknown force r, and which we may require in the torque equation, but here I chose the torque about point O, so that the moment created by r about point O will be 0, which will not appear. And this I could do because the point O is not moving. If it was moving, then I shouldn't have done this. I should ideally choose the moment about G. Then of course the force R, the reaction force, will create a moment. To solve that, I need to consider the force balance equations as well. I hope that is clear, not confusing you. If please, then let me know, I will repeat that again. So I hope that is clear. So we'll move to the next problem. So below is an L-shaped bar of mass 0.5 kilogram. Each of the link has 0.25 kilogram mass. Is lying motionless on a frictionless horizontal surface, and 50 kilogram Newton force is applied at the corner A. Determine the magnitude of initial acceleration of point B. So neglect the thickness of the bar. So thickness in the sense that this thickness, okay, because already it's a two-dimensional system. The extent of the body in the perpendicular plane is anyway neglected, and also they ask him to consider this thickness of the bodies. TA and TB are small, or just neglect them. So try to draw the free body diagram, then I'll explain. We could ideally try solving this, but it will take a longer time, and we have time constraint. But anyway, parallelly you can try solving. I am not giving a lot of time to solve because we have constraints, and all the problems in this particular chapter will be a little longer. So yeah, at least try to draw the free body diagram and check correct or not when I draw it. So you can think of it as just two bars. Okay, one bar here, another bar here. This is 10 centimeter, or you can think 0.1 meter, and this is 0.12 meter. This corner is A and this corner is B, and you have 50 Newton acting here. That's all. That's a free body diagram. Okay, because it's on the plane, the reaction should come from the bottom, and we are considering only two-dimensional system, so we don't need to worry about that. That will be creating, like, the weight of this body is acting on to the plane, and there will be a reaction equal and opposite to that, because there is no other motion is happening on the plane, so it will be just the reaction force equal to the weight. So, but that direction we don't need to consider. Just this much is there. So now we just try to write the force balance equation. So the net force acting is equal to the total mass times the acceleration of the center of mass. So you see there is a 50 Newton acting in the x direction. Should be mass times. So the mass of the body, you can see it's 0.5 kilogram, right? So it's 0.5 kilogram times the acceleration in the horizontal direction. Let's say this is x direction and this is y direction. Okay. So you will get acceleration of x is 100. This is basically acceleration of the center of mass. Okay. Yeah, I think I should write it like x center of mass in the x direction, in the I cap direction. And if you try to write the y equation balance, y force balance equation, and you see there is no force in the y direction, and there is no acceleration because of that. So the y direction, there is no acceleration. So this is the acceleration of the center of mass. Now, but we are asked to evaluate the acceleration of point B, which is not the center of mass. So what will happen is that if you have applied the force 50 Newton along the center of mass, it will just try to slide, all the body try to slide with the same acceleration. But because the 50 Newton is applied offset at point A. So now still we don't know where is center of mass. From the mass distribution you can assume it will be somewhere here, right? Because there's some 0.5 kilogram mass is at this end, and there's a 0.25 kilogram mass there and 0.25 kilogram mass here. So the center of mass will be somewhere at this location. So because the force is offsetted, you can see there will be clearly a rotation happening because of that moment. So that moment will cause it to rotate. That will create an acceleration at angular acceleration at point B. Because of that, along with this translation acceleration, the additional rotation acceleration will come. Total acceleration will be vector sum of the both at point B. Center of mass will not rotate, so center of mass will have only this acceleration, but we are asked to evaluate the acceleration of point B. Okay, so it will have the rotation acceleration. So we have to basically evaluate the rotation. So for that we have to consider the torque balance equation. So we will write the torque equation. So net torque is equal to I times the angular acceleration alpha. And now because there is no fixed points, everything is moving, so we have to write it about the point G. For that we have to first evaluate the location for G. Now again we draw the bodies here. Consider a coordinate system. Let us choose this is purely for the purpose of evaluating the center of mass. So let's choose this being the capital X direction, this is the capital Y direction. Okay, and origin being at the corner of this body, and you know the center of mass of the first body is center of that body, and the center of mass second body center of its that body. Okay, so so the x bar is m1 x1 bar plus m2 x2 bar, the whole divided by m1 plus m2. So the mass of the first body, let's say this is the first body and second body. So the mass of the first body is 0.25 kilogram times x1 bar. So x1 bar is the distance from this origin O to the point 1, which is center of mass of the first body, and you know it's the half of the 10 centimeter, just 5 centimeter, right? So I will write 5 centimeter plus mass of the second body, which is again 0.25 kilogram times x2 bar. Now you see the point 2 measured from O, how much distance apart in the x direction. You can see that 0 distance because they are on the same line, divided by the total mass, which is 0.5 kilogram, and you will see it's just 2.5 centimeter measured from O. Similarly, you can see y bar, which is m1 y1 bar plus m2 y2 bar, the whole divided by m1 plus m2. Again the same 0.25 times y1 bar. Now the point 1 and the origin O, they are on the same y line, right? So they will have y separation being 0. m2, which is 0.25 times y2 bar, which is the point 2 from the origin O, which is half of the 12 centimeter, which is 6 centimeter. So it is 6 centimeter, the whole divided by total mass, which is 0.5, and you will see this is going to be 3 centimeter. So this is just the center of mass calculation. So now we have located the center of mass. so it is at x bar and y bar measured from the point O. So this is the point O, so it will be somewhere here, G. You can see it's in the x direction it is 2.5 centimeter, and in y direction it is 3 centimeter. So this distance, which is y, which is 3 centimeter, and the x direction, sorry, in the x direction, that is this, which is 2.5 centimeter. Now we have located G about point O. Now we come back, so we can mark the location of G, which is somewhere here. So you can see it's outside the body actually. Okay. Now marking all the distances. So I'm also marking center of mass of the other bodies as well, which is exactly at the length by 2 locations. So now let's start evaluating the torque about the center of mass G, total moment about the center of mass G. And you can see only the force 50 Newton is going to create a torque, right? Because that's the only force that exists. So we didn't choose any direction for alpha, right? We know the body is anyway going to rotate about this way, so we'll create a anti-clockwise moment. So we will choose the anti-clockwise moment to be positive. So the torque about G will be due to 50 Newton. It's an anti-clockwise moment, and it is the distance, the moment arm, which is basically this distance, right, about the center of mass, which you can see. So you can see from A, so this is a point O we were thinking, right? So A to O, the distance is 12 centimeter, the corner. Now O to G is, so we know A to O is 12 centimeter. O to G we have just evaluated, which is the y bar, which is 3 centimeter. From this, if you subtract the both, you will get the distance AG, which is actually 9 centimeter. So this distance is 9 centimeter. So 9 centimeter, so it's a 9 into 10 raised to minus 2 meter. So you will get it's a 4.5 Newton meter, which is a torque in the counterclockwise direction. Okay. Now I about G is need to be evaluated. So moment of inertia about G. Now we have two rods actually. One end is A and another, one arm is A and another arm is B. So moment of inertia due to both need to be considered about the center of mass G. Now let's denote the moment of inertia. Okay, let's center of each of them. Let's call this is C1, or let me call this is C and this is a D, which is center of each of the rod. Okay. So moment of inertia about G, from the contribution comes from each of the rod. Okay. So first of all, the moment of inertia of C, or let's say the first body about G. So the moment of inertia of the second body about the center of mass. So what I call by the first body and second body is that the two arms. Okay, both will have a contribution. Because they are just a rod, we can directly add it. The extent of the bodies doesn't matter, only their length matters. Now the first body has a mass of m. Now first body has a center of mass C, right? So I1 about C plus mass of the first body times the distance to the G, which is this is d1. So m1 times d1 square. This is the parallel axis theorem. This is I1 with respect to G plus now I2 with respect to G, that is the moment of inertia of the second body or second term about G. Now this again by the parallel axis theorem you can do it by I2 about its own center of mass, which is basically D. Okay, first you evaluate that plus mass of that second body times d2 square, which is the distance from the center of mass of the second body to the center of mass of the system, or the point where you want to evaluate that. So that is just d2. So I come back here, we need to know I1C, that is like the rod is the first body, its moment of inertia about its center of mass C, the individual center of mass. So it's actually, I have mentioned earlier, it's ml square by 12. So mass of the first body times the length of the first body, ml1 square by 12 plus m1 times d square. Now d1 square, d1 is, see L1 is given, L1 is actually 6 centimeter. I am not substituting that. L1 is already known. L1 is 6 centimeter, sorry, not 6 centimeter, 12 centimeter, the length of the first rod. And L2 is also given, which is the length of the second rod, which is 10 centimeter. Okay. Now D1 and D2, the distances we need to evaluate. Now we can use the Pythagoras theorem for that, because so this distance we know, which is 2.5 centimeter. We just evaluate this center of mass. And O2C, this distance we know it is 3 centimeter. We evaluated that. Oh, sorry, not O2G is 3 centimeter. We evaluated that. O2C is just half of the 12 centimeter, right? It's a 6 centimeter. So if you subtract the both, you will get this distance to be a 3 centimeter. So it's 6 minus 3 is 3 centimeter. So D1 will be just 2.5 square plus 3 square root. D2, come to D2. D2 is also, again you can evaluate it. It will be also around, it will also be same. This distance is 3 centimeter and this distance you can find it is 2.5 centimeter. Okay. Using that D2 will be again the same value. You can substitute them here. So it's m1 L1 square by 12 plus m1 D1 square plus m2 L2 square by 12 plus m2 D2 square. Okay, so here all of the quantities are known. m1 and m2 are same, which is 0.25 kilogram. L1 is given, which is 12 centimeter. L2 is 10 centimeter. D1 and D2 you can evaluate here numerically. Everything is known. Remember, centimeter you have to convert it to meter before doing the calculation to get the correct value. And you will evaluate it to be around 1.271 into 10 raised to minus 3 kilogram meter square. Now Ig is evaluated. So the equation is torque about G is equal to Ig times alpha, and you will evaluate alpha is equal to torque by I alpha, and you will get alpha being 354098 radian per second square. Okay, so now you know the angular acceleration. Now but our objective is that find the acceleration of point B. So we already know one of the component will come from the acceleration center of mass, because B is also, so that probably will write the expression, kinematic expression. Acceleration of B is acceleration of the center of mass plus acceleration of B with respect to the center of mass G. Now acceleration of g we already know, which is I use the notation center of mass. Probably I will write g. Okay, so acceleration center of mass is already given, which is 100 I, which we already evaluated, 100 in the x direction. Now acceleration of b with respect to g, which is, you can see about g, the point b is rotating, right? Pure rotation, which is the distance bg times alpha. Now this you have to be careful. You have to take the vector sum. It's alpha cross rbg. Okay. Now alpha vector you have to appropriately do that vector addition. Pictorially I can represent that. That will be probably easier to understand. So you have two of the bodies, and you have the center of mass located here, and this is the r vector. So because of an anti-clockwise rotation, this is point B and this is point A, the acceleration of B with respect to G along this direction. And this direction, acceleration of the center of mass. See, I represent AG there because G only having AG, but the point B will experience AG, the translation, along with the center of mass, plus a rotation, which is acceleration of B with respect to G. So now you have to take the vector sum of the both, and you can see they are not in the same direction. This angle is theta, and this angle you can evaluate because the dimensions are given. And either you use this expression to evaluate ij, or you can just pictorially find the direction and do the vector sum of both the values. Just the magnitude is known, direction you have to direction is also known, but you have to take care of during the vector addition process, so that you will get the net vector result of acceleration of B. So what is asked is its magnitude, so you can just evaluate it is using the vector addition law, which is, so if I say the magnitude of acceleration B with respect to G, just a magnitude, you will get around 286.03 meter per second square, and the acceleration of G magnitude is already known, which is 100 meter per second square. So you can evaluate the magnitude of the both, which is the cosine law you can use for this, a1 square plus a2 square plus 2a1 a2 cosine of the angle between them, and then take a square root. Just that the cosine of angle between the both need to be taken care of, and you will get it is 265.6 meter per second square. So this is how you do it. So I am not working out everything because we have a time limitation, but I am just explaining how to do that. I hope you will try this out and check whether you are getting that same result or not. Any question here? So I'll probably explain one more problem. So not a detailed explanation, I will. So basically we have a block which is hung like this. Now it is in static equilibrium, right? Now this is broken. Immediately what will happen? What will be acceleration? What will be, so basically we have to evaluate the tension in the string AC at that instant. So you have to try to draw the free body diagram. Okay. So intuitively think what will happen. Not to draw the free body diagram, but you have to think what is going to happen for this. So the system was in equilibrium, and suddenly the right string is broken. Now what will happen? Okay, this is aside. You have to draw the free body diagram, which has nothing to do with this. I mean, not nothing to do, but some relation with this. But you can think what is happening that we may use when we are writing the force balance equations, equilibrium equations. So we have center of mass somewhere here. Through the center of mass, its weight is acting, so which is 5g, and this will have a tension T, and this will have a tension T, 30. Let's call theta, and theta is 30 degree. So now T cos theta and T cos theta will balance. T sin theta and T sin theta will add up to 5g. That's what we do when we do the statics. Okay, now it is dynamics. Already the string is broken, so on the right hand side there is no string at all, there is no force at all. Now this is the free body diagram. Okay, now you know the T cos theta, T sin theta and 5g are opposite direction, so they can get balanced, but because this is a motion, this will not just get balanced. There will be an acceleration in the y direction, and you know intuitively the center of mass, which is g, will move with an acceleration ay, let's say, in the vertical downward direction. And we can also see the T cos theta component, which don't have a balance in the x direction, so it is not equal to 0, but it will create an acceleration of the center of mass in the x direction. So because of this, there will be a resultant acceleration this way to the center of mass, and you know the body will anyway move in that direction, at least the center of mass. That intuitively you can think, right? When you cut one of the string, it will anyway try to move not just vertical down or not horizontal down, it will have an inclined motion, center of mass, but along with that it will have a rotation as well. Okay, so now intuitively you know it is going to rotate in the clockwise direction. I will represent the alpha in that direction, and you also know the string AC is going to rotate with an angular acceleration beta. Let's say I'm just denoting beta, and that will be a counterclockwise acceleration intuitively. But you don't need to specify the direction, as I mentioned, just a convention. Just specify it, and if it happens to be positive when you solve, then okay, the direction you choose is correct. If not, then okay, it's wrong, then you correct it. That's all. Nothing wrong with the convention. Just keep follow the convention, whatever you chosen to. That's all. To write all the expressions. Now again we here write the force balance equation, sigma F. The net force is equal to mass times acceleration of center of mass. So you have the horizontal force T cos theta, which will be just mass of the body times acceleration in the x direction. Remember theta is known, so I should put the value here. So T cos 30, and the vertical force is T sin 30, which is acting upward. I chose the convention of the acceleration to be downward being positive, so minus T sin 30 plus 5g is equal to mass times acceleration in the y direction. Whether mass is given, yeah, I think it's given, so I should put mass as also 5. So two equations, we have 3 unknowns. So t is an unknown, ax is an unknown, ay is an unknown. We cannot just solve it, so we have to write the torque balance equation. So here there is a fixed point C. but which is not in the body. I mean, we can write about C, or you can write about the center of mass G. So both ways you can try, and I will just write about the center of mass G. So 5G will not create a moment. Okay, so because I had chosen alpha to be clockwise, so I'll choose the clockwise moment to be positive. So t cos theta is going to create a clockwise moment. So t cos 30, and the moment arm for that is this distance, right, which is 30 by 2, which is 15 centimeter or 0.15 meter. Now again t sine 30 is also creating a clockwise moment. So t sine 30, but for that the momentum is half of the 60 centimeter, that is this distance, which is 30 centimeter or 0.3 meter. And the 5G, which is weight acting through center of mass, will not create a moment. So this is a total moment. This should be equated to Ig times alpha. So this is a okay, numbered it wrongly. So second equation, and we have third equation. So here t is an unknown and alpha is an unknown, but again Ig came, so we need to know what is Ig. That is a moment of inertia of this body about the center of mass G. Now I mentioned earlier, Ig will be m times L square plus, or let's say B square plus H square, the whole divided by 12. Now remember here B breadth is 30 centimeter, height is 60 centimeters, so just square them and anyway convert them to meter before that. You will get an Ig value. Let me write the number. It's 0.1875 kilogram meter square. Okay. So now you have 3 equations and 3 unknowns, so you can clearly solve for Ax and Ay. Okay, I forgot one more unknown. So there is an alpha. Now the fourth unknown is came, but you have 3 equations, so you cannot just solve the 3 equations. Okay. Now you have to use the kinematics. So kinematics is that let's consider the point A. So you can do it in different way. One of the way I think is good is that consider acceleration of point A, which is acceleration of point G plus acceleration of A relative to G. Now acceleration of G we know it will have an AXI and AYJ. Of course they are unknowns, but we are going to relate it anyway. Plus acceleration of A related to G, which we know give me a second. Yeah. Acceleration of A related to G is a rotation, right? So which is the alpha vector cross RA related to G. So RAG is this position vector that you can determine because all the angles are known, and alpha is already okay, alpha is unknown, keep it as an unknown, and you will get an expression for acceleration of A. Now again acceleration of A you can write from about the point C, which is a fixed point. So it is acceleration of C plus acceleration of A related to C. Now you can see, because c is a fixed point, its acceleration is 0, just the relative acceleration will come, and you know it's pure rotation, right? So you will just have beta, which is we chosen to be the rotation acceleration, the acceleration for the string beta cross with RAC, where RAC is this vector. RA related to C, so the point should be this way. Yeah, so this is RA to G, this is RAC. Now here beta is an unknown. See, RAC both are known. So now if we combine both the equation, you will get AXI plus AYJ, because left hand side is equal for both. If you now we get the right hand side, plus alpha cross RAG is equal to beta cross RAC. Now you have one equation, but it has two component equations. It's actually two equations are there. Two component equations. Now extra one more unknown came, beta. All other unknowns already were there. AX, AY and alpha were already there, but one more unknown came. But we have two equations. So earlier we had 3 equations. With these 2 equations, total we have 5 equations. And the total unknowns, you can see earlier AX was there, AY was there, T was there, alpha was there, and now one more unknown, beta came. Total 5 unknowns, 5 equations. Simultaneously you can solve all of them to obtain each of the values. So I'll just write the values. You'll have AX being 2.6 meter per second square, AY is minus 8.31 meter per second square, alpha is 22.4 radian per second square, beta is 29.4 radian per second square, and tension is 15 Newton. AY is actually plus, because we chosen everything according to convention. So you are getting everything plus, that means the assumption we made is correct. It will have a horizontal acceleration, the plus x direction, and vertically down it have an acceleration AY, and then tension is acting, and then all the alpha and beta values we have chosen is correct. So that's how you do this problem. Any question here? So if there is no question, we will stop here for today. So we'll meet next week. Thank you.